Hello and welcome back to my office where we're going to talk about irrotational flow. And today we're going to talk about lifting line theory. And let's see here. The objective is to lay the foundation for aerodynamics. So really we're going to touch on a lot of what people would consider aerodynamics, and we're going to stop. We could go on and on with this development of lifting line theory and panel theory and on it goes. But I thought I'd give you a little taste because it is an irrotational flow solution and it generates one of the more famous equations in fluid mechanics, namely that the lift of a thin airfoil is 2 pi alpha. So I think it's worth seeing that derivation as part of the irrotational flow module, but we're going to touch on a lot of these topics again when we talk about external flow. So what we're going to do today is introduce the Kutta condition, which is also fundamental as a concept within fluid mechanics. And then we're going to develop the theoretical lift for a flat plate, and then I'm going to compare it to data, right? Because what's theory without experiment? All right, so the Kutta condition. So the Kutta condition is a requirement that the flow around the body meet at the trailing edge and be tangent to the chord line. So let me show you some examples. Here is a body. It's a thin symmetric airfoil, and it has a stagnation line in the front and in the back, and the chord line goes right through the center of the airfoil because it's a symmetric airfoil. You can see that the stagnation streamline strikes the leading edge and then it departs from the body at the trailing edge. And the velocity normal to the chord line is 0 at the trailing edge. So here is a unsymmetric airfoil, and the chord line for this unsymmetric airfoil should go from tip to tail, all right, something like that, but a straight line. And you can see that this leading edge stagnation hits the tip of the leading edge of the airfoil around the chord line, but the trailing stagnation point is upstream of the trailing edge. So the Kutta condition says that that stagnation line should be at the trailing edge, and not only does it need to be at the trailing edge, but it needs to be aligned to the trailing edge, aligned to the chord line. So it needs to look something like this, right? This is the Kutta condition, that the velocity emerge from the trailing edge and that there be no velocity in the cross-stream direction. So it should look something like this, right? So this airfoil does not satisfy the Kutta condition, or this flow field, I should say, does not satisfy the Kutta condition around a non-symmetric airfoil, but this one does, right? So the Kutta condition means that the velocity leaves the trailing edge, TE, the trailing edge, of the airfoil aligned to the chord direction. So the velocity in the normal direction, or sorry, in the streamwise direction, in this case U, the streamwise direction, is not 0, whereas in the cross-stream direction at the trailing edge, it should be 0. So that's the basics of the Kutta condition. And how do we enforce the Kutta condition? We add circulation. So if you go back and you look at this airfoil here, if I added some circulation around this airfoil, a vortex, you can imagine I could push that streamline back to the tail. So that's what we're doing here. We're going to add circulation to the airfoil. What's the justification of that? Well, the justification is that we really do have circulation around a lifting body, and it starts from when we start the airfoil. So there's this idea that vorticity is conserved, so that if I begin the airfoil, and the airfoil, if I begin the motion of the airfoil and it has lift on it, then it will have circulation. But in order to conserve circulation, there should have been a counter-rotating vortex somewhere else. And that happens upon startup, right? So there's this starting vortex that emerges from the flow field when the flow begins. And what we do is we ignore this starting vortex, and we our domain of influence is really here. And so really when we look at the circulation around an airfoil and we draw this box and we follow our line integral around, we're really ignoring this starting vortex, but it should have the same vorticity or circulation gamma that is around our airfoil. So that's the balance of vorticity within the flow field. And if we know what the circulation is resulting from this startup vortex or the circulation around the airfoil, then we can calculate the lift. Right. So I have this crazy video here by Ludwig Prandtl. And let me start it over here. There it is. Anfahrt eines Tragflügels. So that means the driving of a wing. The word Anfahrt in German, the root word is Fahrt, which means to drive or to go. So you could see the startup vortex leaving the trailing edge of the wing, and you can see the separated region. Watch carefully here. Here we go. Yep, it starts up. There's our trailing edge vortex here, leaving the flow field. So now this wing has circulation around it, which results in this idea that there's lift around the airfoil. And you can see the wake. And if you look carefully, you can see, if you believe, the Kutta condition. Der Anfahrtwirbel, so this is the driving of a swirl of a Trag wing. I don't know what Trag means, but so they're gonna drive it, and the camera is gonna be, it said mitfahren, so the camera is gonna stay there with it. No, mitstellen it said, right? Yeah. So there is that vortex, the trailing edge vortex. The wing takes off, and this time, because we're in a stationary frame of reference, we can see the vortex. Oh, can I pause that? So this is a video, a short video showing the counter-rotating vortices. They're going to start it, they're going to go a short distance, and then they're going to stop. Start, stop. And so you can see when they started, we had our starting vortex, and then when they stop, all of that circulation gets shed again as a vortex. So those should be counter-rotating vortices that have the same magnitude. There they are. This represents the circulation that was around the airfoil, right? That was generating our lift, and this is the equal and opposite vortex that gives us this conservation of vorticity, so to speak, in this irrotational flow. With a lack of a wall, there's no way to generate vorticity, which comes from the shear stress. But getting ahead of ourselves, we'll talk more about that in boundary layer theory. All right. So I can't go on. That video that I just showed you was by Ludwig Prandtl, one of the greats of fluid mechanics. So here he is as a relative young man, 29 years old, and the hero of the day. Believe it or not, he's got there a water table, and he was really innovative with experiments. And if you didn't know, he was the one that proposed the boundary layer, the no-slip boundary condition, and everything that results from the no-slip boundary condition. So that was in the early 1900s. So right around the time this photo was taken. I think it was 1905 actually, but or 1909. Either way, right around this era, he solidified the idea of the no-slip boundary condition amongst the world of in fluid mechanics. Here he is in 38, so that's, wow, that's 34 years later. And he's inspecting, this is him right here, this guy with the beard in the middle. He's inspecting a Ho-3 airplane, which as you can see in the back there. It was an airplane that was used, in a competition in Germany for flight and maneuverability. And here he is after the war. That's him, as it says here, pictured in Germany in 45 with Dryden, as in NASA Dryden, with Prantl, there he is, with von Karman, there's von Karman, who started JPL and was a student of Prantl, and then Shin, who was at Caltech and eventually worked in the department that von Karman worked to start. So, cool picture of some greats in aerodynamics. And this is my favorite picture of Prantl. He's at a water table. This is a water table. He's looking down, and see, this is the actual water channel here. This is the contraction section. So the water comes in here, and a lot of those images that you just saw, or images that I've shown previous with the hydrogen bubble and all of that, could have been generated in this table. He's got a pipe there in his hand. Is that a pipe? I think it is. Maybe it's something that he uses to squirt some dye in there, but pretty cool photo. All right, so he didn't work just in fluid mechanics. He really, he worked in elasticity and plasticity and rheology, the boundary layer, as I said, and fluid resistance, turbulence, and this idea of vorticity within turbulence is called eddy formation, gas dynamics, compressible flow, wings. Just a huge body of work from a really active researcher and scientist. And even this picture that everyone is very familiar with is called the Prantl-Gaut singularity. And it's not from a shock wave, right? It's from condensation of flow across a pressure difference. But it's often miscited as being the result of breaking the sound barrier. All right, all of that aside, I almost forgot what we're talking about today. So let's see. We're talking about the vortex sheet, right? So we're going to do the finite length vortex sheet with a free stream so that we can calculate what the theoretical lift of that vortex sheet is. So let's recall what the infinite vortex sheet looked like. It was an infinite row of vortexes aligned in the xz plane. They all have the same strength K separated by a distance A. And it generated this really cool looking flow field. This is the near field where you can see the vortexes and you can see the saddle points where the streamlines appear to cross. They just come together and they separate. And this is the stream function that describes the overall flow. And then in the far field, if you recall, we zoomed out and we solved in the limit as x and y go to infinity what the velocity is in the far stream. The u velocity and the v velocity was 0, right? So we end up with this parallel shear flow, basically. The circulation we calculated, and we introduced this vortex strength. Now in this problem, each vortex has the same strength, k, right? And k is equal, so you end up with this simple expression, 2k pi a. And then we could calculate any lift by looking at the circulation times rho times u infinity. But the problem that we're going to take on today is that the plate doesn't extend to infinity in the xy direction. It's bound between 0 and the chord length. And as a result, we're going to have to enforce the Kutta condition, which means we're going to have to enforce that the velocity at the trailing edge be 0. And that means ultimately that this value of k is going to have to be a function of x, right? So that is our task today, is to find that. So here's our basic picture. We've superimposed a free stream with a series of vortexes, and we're kind of assuming that it's a continuum, right, of vorticity along the x-axis. But as I've drawn it here, the strength of this vorticity varies with x, and that's what that gamma function represents. So it's superimposed a free stream with a finite length, no thickness vortex sheet with variable strength, right? So the k value is going to vary along that. And if you want to see more of this, you can have a look in Frank White's book in Fluid Mechanics. That has a very nice treatment of this, as do a lot of other undergraduate and graduate books. All right, so that's the basic geometry. And we imagine that this vortex is going to generate some upper and lower velocity in the xy direction. And the free stream is also relative to this angle alpha, so I have some sort of angle of attack built into this. So the requirement specific to the finite length plate is that we satisfy the Kutta condition, right? So that means that the velocity, the upper and lower velocity evaluated at the chord length needs to be 0. So this really should be maybe at x equals to c, the chord length, right? That's the Kutta condition. In terms of the strength of the vortex, that means that gamma, the strength of the vortex, which is defined as the velocity difference between the upper and lower plate, again, this probably should say at x equals to c, needs to be 0. All right, and in addition, we also have to enforce that there's no velocity through the plate, right? So you can't have a velocity through the plate, so that the v velocity near the plate is 0. All right, so this would require that at y is equal to 0 along the plate, the free stream velocity plus the velocity generated by the vortex, I should say, you know, the y components of those velocities need to be 0, need to sum to 0. So what we need to do is to find this vortex strength, gamma, that makes all of that happen. So really what we're trying to do here is solve for gamma. Let's recall from the very basic definition from our building blocks how we derived what the vortex is. We said that it was some gamma over 2 pi, and if you remember, I also had it listed as k over r, right? So those were kind of interchangeable definitions. So gamma over 2 pi over 1 over r. So that's our inversely decaying vortex that only has a component in the theta direction. And keep in mind here that we need to generate a slower flow under the plate, right? So when so I have reversed the rotation of the vortex, right? So normally it's right-handed, so it should rotate counterclockwise. But what we need here is we need this vortex to kind of retard the free stream so that we get lower velocity on the bottom of the plate and higher velocity on the top of the plate, which results in a pressure difference, which results in the lift force that we're going to get. So keep in mind that there could be a negative sign that you're not expecting coming in here associated with this gamma here. All right, so now consider this infinitesimal line length dx associated with the line vortex. So if I had a line length dx, then dx times minus gamma would be equal to the circulation. And I think really we showed that last time if you just go look at how we sum the circulation around the flat plate. The velocity then this velocity here, or the infinitesimal velocity at the plate, so at x, is now this differential velocity v in the cross-stream direction is equal to this differential gamma divided by 2 pi r, where r is being evaluated at the location of our little infinitesimally small line segment x. So r is going from, is being evaluated at x naught in the, extending into the x direction. So it's the influence of this little line segment on the y velocity locally. So just substituting this into there, I get this expression wholly in terms of x. So I can integrate this expression to solve for what the vortex, I can integrate over the length of the sheet from 0 to the chord length of this expression to get what the induced velocity is of the sheet as a function of x, if I knew what gamma x is. But this is my first equation for gamma of x. If I take that gamma of x and I say that, as we mentioned before, that the velocity in the x direction generated by the vortex sheet, what did I say? The velocity in the y direction generated by the vortex sheet must exactly cancel the y direction velocity from the free stream. So that's what this is. So I'm adding the free stream here. This is the free stream with the vortex. So those two y component velocities sum to 0. But it gives me an equation for gamma of x, and that's what we're after. So I need to solve this integral equation for gamma of x, so I need to differentiate. Now, the boundary condition with this differentiation is going to be that the value of gamma at x equals chord is equal to 0. So that's our Kutta condition requirement. Now, this is a non-trivial integral to differentiate, so I'm not going to ask you to do it or do it here, but it is done out in Anderson. That is one place that you'll find that Anderson's got a couple of very nice books that he's written. I know that he's got a CFD book, and then he's got this Fundamentals of Aerodynamics. They're both in paperback, by the way, so they're cheaper. But this step is done, I believe, in Anderson's book, so you can have a look. And anyway, here's the resulting, that's what we've been after. So this is the value of the vortex strength such that we get a finite line length that satisfies the Kutta condition when superimposed with a free stream with an angle of attack. So from here, we can calculate the lift, because if we know this, then we know the local velocity field and we know the pressure then. So let's proceed with that. So here's our picture again. And the coefficient of pressure on the upper and lower, so that's what this U and L means, upper and lower. The coefficient of pressure for the upper and lower is the pressure along the upper and lower sheet minus P infinity, the far field pressure, divided by the dynamic pressure of the far field. So that's our standard definition of what coefficient of pressure is. And then we showed not so long ago that this is related to 1 minus the magnitude of the velocity at the upper and lower portion of the sheet divided by the free stream velocity. So I can calculate this velocity magnitude along the upper and lower by just looking at the vector components, right? It's going to be, this is the free stream x velocity, this is the vortex velocity that we can solve, and then this is the y component of the free stream velocity, which we know is 0 for the flat plate. So I can turn the crank here and expand this. I can FOIL that out, and if I make the assumption that this term here, because I know that u is small compared to big U, or that's the assumption anyway, then I can get rid of this term. And then if I make the small angle approximation that cosine alpha is 1, I can simplify and get rid of that cosine alpha. So I'm left with this expression right here for what the magnitude is, or the magnitude squared of the velocity just above and below the plate. So if I put that into my coefficient of pressure, blah, 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 and I turn the crank, I end up with just this gamma x over u infinity. All right. So if I want to calculate the lift, then the lift is just the integral of the pressure from the upper and lower, right? You just sum up the pressure difference between the upper and lower portion of the plate times the width of the plate, and that'll give me the lift. This should not be set equal to 0 because we're going to get some lift here. So if I define it this way, and then if I divide this lift by my dynamic pressure times the area, pressure times area is lift, then you will get a dimensionless lift force. It's unfortunate here, D and W are the same. They're both the width into the board here. I think I stick with D for the rest of that. That's the span width of the airfoil. So here's just the integral, and I put in the coefficient of pressure, and I stick in what we just got on the previous page, that's gamma, and I get this expression. And it's just convenient to non-dimensionalize your independent variable x with c so that I can then change the limits of integration from 0 to c to 0 to 1. So this is with the derivative dxc. So that becomes kind of the independent variable. It's just a slight change or transformation of the independent variables for convenience. So if I integrate this, then I get this expression that the coefficient of lift is 2 pi sine alpha. And if I make a small angle approximation for sine alpha is equal to alpha, then I get this famous expression, that the coefficient of lift is 2 pi alpha. All right, what a triumph. So in summary, we have that the theoretical lift on a flat plate immersed in a free stream, and I've kind of just changed the drawing here, so now I got the free stream drawn horizontally with the plate making the angle of attack. The lift coefficient is 2 pi alpha. Again, that's a big result in the world of fluid mechanics, that we could calculate this theoretically. Where is this force, though? Well, it acts at the center of the moment, and so we can calculate the moment arm just by multiplying by x within our integral for force and get the moment arm. And so it turns out to be 1/2 CL. So that means that the moment is located at x divided by c. That's the center of pressure. So that's what the CP is. Center of pressure is 1/4. So it means that my coefficient of lift is 1/4 from the leading edge. And keep in mind, this is independent of alpha. So this thing is just stuck there at whatever angle alpha makes. All right. So let's look at how good all of this is. Let's kind of compare it to experimental data. This is a picture of a flat plate immersed in a free stream where here the free stream is moving in horizontally and the flat plate is pitched at some angle of attack. And the first thing that jumps out at you is the symmetry of all of this flow, right? I mean, it's totally symmetric about this line here. And as a result, it does not satisfy the Kutta condition, right? The Kutta condition would say that this thing has got to come out straight like this, right? That the velocity has to be aligned to the chord length, and the velocity normal to that chord length needs to be 0 at the trailing edge. So for creeping flow, which is what this is, this Healy-Shaw flow, it does not satisfy the Kutta condition, namely because there is no net circulation around this plate. This plate is not generating lift, right? Here's another example. I got both of these two out of that album of fluid motion from Van Dyke. So again, this is Healy-Shaw flow, so this is very slow flow where you've got basically no wake. That's kind of a tip-off that it's a very slow flow. And again, it says, this is dye and oil streamlines, potential flow past the NACA airfoil at 13-degree angle of attack. However, because the Healy-Shaw flow cannot show circulation, the Kutta condition is not enforced at the trailing edge. So you can see here it looks like the flow is kind of doing what we said it was going to do earlier. It kind of shoots off the airfoil trailing edge here, so that's not what we want. This is more like it here. This is showing a flat plate inclined just slightly 2.5 degrees to the free stream. There is a recirculation bubble here as a result of separation, but you've got laminar, so it reattaches here, and it's basically laminar flow along the top, and then it reattaches here, and you can see this really cool, swirly, turbulent flow. But in either case, it's much closer to the Kutta condition where you've got this trailing edge that's aligned to the chord length. This is some stills from Prantle's work here. You saw the video, and the video was way cooler, but I thought I would just show the stills with this particular instant in time where it looks like we're doing a pretty good job of matching the Kutta condition there and coming off here, although it turns not long afterwards. I think I've showed this video before, but I'll show it again. This is from the National Science Foundation. This is this whole National Committee on Fluid Mechanics, and they conscripted a whole bunch of really famous folks to work on these, so they're really a pleasure to watch. Just beautiful fluid mechanics. I mean, look at those streamlines. You would be hard-pressed today to generate this flow field anywhere, really. So look at that stagnation streamline. It is bang on in the airfoil trailing edge, and then you can't see it on the back. I'm not sure why, actually, but you can see that the wake is almost completely closed. And then here we are moving up in angle of attack, and you can see the wake and the separation. And so are you convinced that we're following the Kutta condition here? It looks like we're doing a pretty decent job with this lower level, right? Those streamlines are just right there on that trailing edge. All right, very nice. Here is an irrotational solution that I generated, and you're going to get a chance to generate this later. In the project, I ask you to calculate numerically the flow. And what you're looking at here is there's a flat plate right in here, and then you can really kind of see it. It's right here. So you can see that the streamline, the stagnation streamline, comes in and it hits the plate, and then it leaves the plate right on the trailing edge, and then it's quickly bent and swept downstream. But it does match the Kutta condition right there. And the way that you get that to match the Kutta condition is you need to shift your free stream velocity, and you do that by arbitrarily adding a number to your psi function until you match the Kutta condition. So I'll go into more detail, but that's what you need to do when you do this project, is to shift that free stream. It's not arbitrary when you've got that plate in there and you're trying to match the Kutta condition on the plate. All right. So here's some data. Here's a NACA 0012. So it's a thicker airfoil. It's not crazy thick. It's 12% thick, and it's 00, so there's no camber. And then this is the cambered airfoil, and then this is the lift. You can see it's a symmetric airfoil because the lift goes through 0 at 0 angle of attack, and then it rises, and then it begins to separate around 15 degrees or so. You get really massive separation, so the lift begins to drop off rapidly, and it just drops off, just falls to 0 after this. And then this is the non-symmetric airfoil, so you get some lift at 0 angle of attack. You'd have to pitch it down to get 0 lift, so you'd have to have negative angle of attack, but it rises and falls, not much unlike the NACA 0012 airfoil. And it's plotted here in angle of attack in degrees and radians, because this 2 pi times alpha is really in radians. So if you plug in 0 radians, of course, you'll get a CL of 0, but if you do the calculations over this range, this is what you get in radians over this range of degrees, I should say. And this is the lift. So let's see, at 0.08, you're getting the lift of about 0.54. So that's pretty darn close, right? So if I plotted a line on this, you can see that's the theoretical lift line. So that's that 2 pi alpha superimposed. So it does a really fabulous job lower off here. And then as separation comes in, what would you expect? You would expect, because the flow doesn't recover, you don't get as much lift, and you end up with a deviation from the theoretical solution. So also, of course, the theoretical solution doesn't predict any kind of stall, so this just goes on forever with a slope of 2 pi. That's pretty good, though, for irrotational theory. So I think I mentioned those two. There is no stall for the theoretical line, and the theoretical line goes through 0, 0. So what if I wanted to include camber, right? So I didn't want necessarily just the flat airfoil. Well, you can go back through the theory that we just did, and what you have to do is you have to move your line off the x-axis, and it needs to now have xy functionality. This graph I lifted from somewhere, it's showing it here as z, but basically I think you'll get the idea. Your gamma function becomes a little more complicated, and you're no longer on the x-axis, you're on some arc length s here defined by this line, z, some function of z. So you can do all of that, and it's done out for you in this Frank White book that I pointed you to. And essentially you get 2 pi times sine alpha, that's what we got before, plus some shift, right? So you're shifting the angle of attack, basically, by this 2hc. Now, it's a bit confusing, right, when you talk about cambered airfoils. This 2hc is the location of the maximum thickness, 2hc, which is equal to 12% for the NACA 2412, right? 24 divided by 12, basically. So when I plot this theoretical curve back on this plot that I just had, you can see we do a pretty good job, right? Really what you're doing is you're shifting, really think of it as just shifting this angle, this line back that way. So a lot of times you'll see it written as beta is just an angle which represents the arc tangent of this 2h over c. So that's this delay in the angle of attack by shifting from 0. All right. Now, if we think about 3D effects, can we account for the 3D effects? So why are there 3D effects? Everything that I've showed you so far, the data and the wing itself, are infinitely long into the board, right? That's the span-wise direction along the wing, the span-wise direction. Real airfoils aren't infinitely long, right? Really, if I say airfoil, I should say wing. The airfoil is the shape of the cross-section. We call that the airfoil. The wing is the three-dimensional shape. So there are no infinitely long wings. And what that does for us is the wing is, here I'm showing a non-symmetric airfoil where you've got higher pressure on the bottom and lower pressure on top. That means you have, due to the Bernoulli effect, you have to have lower velocity on the bottom and higher velocity on top. And the difference in this velocity times the area, the difference in the pressure times the area is what results in the lift. Now, if you had low pressure on the bottom and, if you had high pressure on the bottom and low pressure on top, as you got towards the tip of the wing, flow likes to go from areas of high pressure to low pressure, right? So as you got to the tip, it would just want to kind of circumvent the wing and go around the edge. So this wing is flying along in this direction. There's high pressure on the bottom, pushing up, giving you the lift. The flow would kind of short circuit, right, and just flip around. That's the wingtip vortex. And this is a top-down view. This is a wind tunnel image showing a wing placed in a wind tunnel with some smoke lines. And you can see that as the flow flips around, it begins this swirling motion off of the wingtip. And what it does is, because it flips around and kind of wants to equalize the pressure around the wingtip, it decreases the overall effectiveness of the wing, right? If the pressure were in equilibrium, top and bottom, it means that it wouldn't be generating any lift for us. So 3D effects should lower the overall lift on the airfoil. And so the idea when we do 3D irrotational flow theories, we're going to have this vortex that rolls up on the tips. That's kind of a nice image. And we're used to seeing, wingtip vortices on airplanes and so forth. It means that our lines that used to extend to infinity, now we have to bend around and bring down into the swept flow behind the wing, and we have to vary the amplitude of the line source by a second function in order to completely account for this effect. So it's just more complicated, a little bit more complicated mathematics here, but the bottom line is, I don't want to go through all the math. It's in Frank White's book, and we're really getting into airfoil theory here, which is a whole topic in of itself. The bottom line is that you reduce the overall lift by 1 plus 2 over AR, where AR is the aspect ratio of the wing, span divided by the chord. So if the span goes to infinity, right, an infinitely long wing, then AR goes to infinity. If AR goes to infinity, then this term here goes to 0, and you just recover the 2D wing, right? But it represents just this shift, and I thought I'd show you some data. Here's some data showing angle of attack versus coefficient of lift for an airfoil, and I don't know what airfoil this is, but it's some non-symmetric airfoil because I've got lift at 0 angle of attack, and you're looking at various aspect ratios. So for very low aspect ratio wings, 1, that's a very stubby wing, right? This wing is only as long as its chord. You have basically low lift. And as the aspect ratio of the wing goes up and up and up and up, the lift increases. So wings that are meant to really soar and glide like an albatross, they typically have long aspect ratio wings, whereas very maneuverable sort of aircraft like a Sparrow has a nice short stubby wing, and it can really maneuver. But again, we'll talk more about that when we talk about external aerodynamics. All right, so this is the data, and if I renormalize the data or just replot it by alpha and use this modified alpha, then you can see I can almost collapse all of the data onto the theoretical line. Of course, not counting roll-off due to separation and stall. But again, you see the same effect. Here's the theoretical line, and the accounting for the aspect ratio of the wing just about collapses all the data onto a single curve. So that's pretty nice. The last topic that we're not going to cover, but it's in the book, and I just wanted to mention that it's out there, is conformal mapping. So one idea, you could spend a lot of time, if this whole class were dedicated to potential flow theory, we would get into conformal mapping. And basically, it's a variable transformation where you take the circular cylinder here and you map it onto a shape. So you can take the circular cylinder and map it onto this z-plane from the psi plane and generate a flow field. So you just wrap the whole flow field around in the same way that we can wrap flow around a corner. We can do the same thing in this complex plane. So you can generate flat plate airfoils, as I've shown here, with camber, or some symmetric airfoil. If you want to see more, it's in this fluid mechanics book by Kundu. There's a whole chapter on aerodynamics where they do this in various shapes. You can improve this and even add camber to a non-zero thick airfoil. Anyway, just wanted to let you know that's out there. So to wrap this talk up, this section, I just wanted to review what we did. We generated the finite length lifting line theory. We introduced the Kutta condition. We then calculated what the lift is for this lifting line, and we found it's not too bad actually for a flat symmetric airfoil over a small range of angle of attack that doesn't include separation and stall. And next time we're going to talk about numeric methods. And the reason I don't do conformal mapping in this class is because I think numeric methods have really kind of overshadowed them. Numeric methods, when you look at them, they were, conformal mapping, it was really developed for pre-computer age, and really with computers we can do a lot more than we could with a conformal mapping, which is limited to the geometries and the shapes. So I think our time is better spent looking at a little bit of numeric solutions, although conformal mapping is still used a lot when generating the meshes for numeric simulations, because they tend to generate smooth, continuous meshes that are orthogonal. And so those are nice things when it comes to building computational domains. Anyway, we'll wrap it up here, and I'll see you again next time. Have a good day.